Okay. Consider a horizontal surface and let's say there is a triangular wedge. Okay. Basically a triangular block. When you see from the side, it looks like a triangle. What happened to this? Right. This block is simply placed on it. It's not a fixed inclined plane. Okay. It's simply a wedge which can move forward or backward. Right. And assume there is a block on this wedge. This is also a very common question actually, but it's an interesting case where we apply what do you call pseudo force. Anyway, let's say this is the situation. One of you tell me, if we simply release this system, okay, wedge, block are both movable, all surfaces are smooth. Floor is smooth and the surface between the block and the wedge is also smooth. What will happen if we release this system?
Sir, the block will obviously slide down.
Okay. What about the wedge, the triangular block that is there? See, the question is what happens to this system? And I have been telling you from the starting of this chapter, from since the starting of this chapter, when you are required to decide or determine what happens to a system, what is the first thing you need to do?
Sir, see what will happen when both of the surfaces are smooth.
No. That is when you are dealing with rough surfaces. Here, all surfaces are already smooth, and you have to find out what happens to a system. So, generally, to find out what happens to a system, what is the first thing you need to do? Anyone? Okay, while solving any problem in laws of motion, what is the first thing we do?
Sir, we check the components
Of
of the block and of the block because
block is an object. Objects won't have components. I want you to be clear there. Anyone, what is the first thing we do when we solve any problem in laws of motion?
the force is acting on the block.
Forces. See, not just because I'm telling you or something. If you ever see, force is what changes the state of a system. You all know that. Okay. So if you want to tell what happens to a system later, you should think of what forces are acting on it. No, obviously, those are the things that will change what happens, that will determine what happens to the system. So you should think in terms of forces. Aishwarya, tell me, what forces act on the rectangular block? Let's take their masses as okay, m and 2m. I'll make this general and let this angle be theta. Actually, we could have taken m1, m2. Anyway, let it be m and 2m for now. Aishwarya, what forces act on the block of mass m?
The weight and normal.
Weight and normal force. Okay. Smooth surfaces, no need to consider friction. And usually when objects are on inclined surfaces, we resolve weight into two components. Aishwarya, can you quickly tell those components?
Sir, mg sin theta and mg cos theta.
Right. mg sin theta will be dragging it down the surface. And mg cos theta will be pressing it onto the surface. And from the surface, there will be a normal force acting on it. Let's call it N. We don't know how much that is. Okay. Do all of you agree with this? Do you think any other forces act on this block? Right. Someone unmuted. Do you want to say something? Okay. Pawan, tell me what forces act on 2M. No response. Vanilla, tell me what forces act onto M.
Weight, normal, and mg cos theta.
Okay, let's be clear. First, its weight will act 2 mg. And since it's on a horizontal surface, we'll show the weight as it is, 2 mg. You said normal force from?
From the ground, sir.
Okay, from the ground, there will be a normal force acting on it. Makes sense. What other forces act on it? Let's call this as N2 and let's call that earlier one as N1.
Normal force from the block, sir.
Okay. Are you sure you want to call it normal force? Earlier you said mg cos theta. What do you want to call it as? Normal force or mg cos theta? రెండు ఒకటే అంటావా?
రెండు ఒకటే, sir.
Okay, so she's saying doesn't matter what we call, they are equal. Okay, but the kind of force is a normal force. The block presses the triangular wedge. Okay, so I'm calling this as block. Most of you will be, must have been used to these terms, but in case you are new, you must have eaten potato wedges and all, no? So yeah. So block presses the wedge. So there will be a normal force acting on it, and that normal force acts this way. Forces acting on the wedge I have shown in green. Forces acting on the block I have shown in orange. And okay. So she's saying we can call this N1, which is equal to mg cos theta itself. Fine, let's assume that is correct. Do any of you want to give any different answers? My question was what forces act on the wedge? Okay, we'll go with this. Just a moment. So if you all are agreeing with this, that means you all feel that N1 will be equal to mg cos theta. Of course, that is what we have been doing all these days. We have been equating N1 to mg cos theta. But just a moment. Let's check that. Because all these days we had, in all the questions that we solved till now, the inclined surface never moved. But this time it is moving. So we'll have to find out whether it will be equal to mg cos theta or not. Let's look at the forces acting on M only. These are the forces acting on it. Okay. Now you all seem to be saying that N1 should be equal to mg cos theta. We'll see. This is the question now. Now let's assume N1 is equal to mg cos theta. Then one of you tell me how much is the net force on block? How much is the net force on the block?
mg sin theta, sir.
Mg sin theta. That will be the only unbalanced force. So it should be mg sin theta. And Vanilla, continue. Due to that force mg sin theta, what should happen to the block?
It will slide down, sir.
It should slide down. And see, there is a clear direction for mg sin theta. So you all indirectly mean to say that the block is going to slide this way. Slide this way means it is going to slide at an angle theta with the horizontal, because incline is making an angle theta with the horizontal. Okay. We still don't know if this is correct or not, but if N1 is mg cos theta, this is what should happen. Now look at the wedge. We have considered the forces acting on the wedge. Let me remove the block. These are the forces acting. There are three forces acting on. Whether this is mg cos theta or not, we don't know, but force will be there. Let's call this as N1 itself. Now you all tell me, can these three forces cancel? One vector pointed upward, one vector pointed downward, one vector making some other angle. Can these three cancel and give zero resultant?
No, sir.
Definitely not. Okay, because upward downward forces may cancel, but this normal force N1, it has a horizontal component. Okay, let me adjust these vectors. These are the forces acting on it. So from the diagram itself, it is clear the x component, the leftward component of n1 cannot be balanced by anything. n1 will have a downward component that and 2mg can be balanced by n2. That's fine. The surface is hard enough, it can support. But who will prevent it from moving to the left? Okay. So do you all agree with this or not? There will be a net force on the wedge to the left. Is this clear or not?
Yes, sir.
Okay. So how should the wedge move? If it is free to move, what will happen to it? N1's x component is the net force acting on it. Obviously, if the force is in that direction, it will accelerate in that direction only. So the wedge will move to the left. It will accelerate to the left. Acceleration of the wedge, I'll call it as A2. Acceleration of block will take as A1. Do you all agree with this or not? When we release this system, the block slides down. Some of you said that, but the wedge doesn't stay there. The block will be pushing the wedge, no? And the force with which it pushes has an x component, which will make the wedge go back. Yes or no? If you have any doubt in this, ask.
So can you explain once more how the wedge moves back?
What forces act on the wedge?
Sir, N1, N2, then
Huh.
2M.
N1 is acting at an angle, right? N1 is a
Oh,
normal
yeah,
force.
sir, I understood.
Huh.
N1 makes it go back. Like.
N1's component makes it go in the backward direction.
Okay.
Right. Okay. Now, there are many questions here. Is N1 equal to mg cos theta? That is one question. Does the block slide making an angle theta? That is another question. And what is the actual question? I just asked you what happens to this system. Some of you said only the block moves, but now it is clear that the wedge also moves. So now what you need to do is calculate accelerations of the block and the wedge. Okay, we'll do it. I don't expect you all to do it right away, but follow the steps. So as I said, if you ever need to decide what happens to a system, first consider the forces. You don't have to assign magnitudes. You don't have to say that N1 is equal to mg cos theta. We don't know that yet. But you can say that there will be a normal force acting. Okay. Again, let me copy paste the diagram. See, these are very important questions. There are a lot of concepts involved in them, so follow thoroughly. Had the wedge been fixed, okay, had this been a fixed surface, we know that the block of mass m would have slid along that surface. Okay, definitely it would have moved, making an angle theta with the horizontal, and under the influence of which force? Under the influence of mg sine theta, it would have moved like this. And normal force would have balanced mg cos theta. How do we know that it is balanced? Like from everyday experience, there is no movement perpendicular to the surface. Means forces perpendicular to the surface must have been balanced. So that way we can say n is equal to mg cos theta, because there is no movement perpendicular to the surface. And that happens when the wedge is fixed, or somehow it is not allowed to move. Okay. But here the wedge is free to move. If it is free to move, you know it is going to move to the left. So I'll have to, okay, how do I show this? Anyway, let's try. If the wedge doesn't move, it follows that line. Imagine the wedge moving to the left, block sliding down, and the wedge moving to the left. Then what will happen at one instant? The block may be here. I'll just take a smaller block to make it clear. And let's move the system to the right a little bit. So at one instant, situation will be like this. Block goes down, wedge moves to the right. So let me take why is this not working? Right. So the next moment, the wedge moves to the left. 1 second. Okay, let's keep it simple. Wedge moves to the left a little bit. Block slides down a little bit. It will be here. Okay. Sometime later, wedge moves further to the left. It is accelerated. Let me use a different color. Okay. And see what happens to the block. Block goes down the wedge. But look at how it is going. So this is what the situation will be like. Had the wedge been fixed, the block would have moved along this orange dotted line. In that case, normal would have balanced mg cos theta because there is no movement along this axis. You can call this as the y-axis if you want. There is movement only along the x-axis. Okay, so in the y direction, the forces must have been balanced had the wedge been fixed. But now it is clear. Wedge is moving and the block is also moving. Then things don't move like how they used to move before. Now the block moves like this. Okay, now if you consider that orange line as the x-axis, clearly the motion of the motion of the block has an x component and it has a y component also. It is accelerated even in the y direction. Now all of you thought n is equal to mg cos theta, but now you tell me, you know that there is a normal force acting on the block. You know that there is a weight component acting on the block. N is there, mg cos theta is there. Are they equal? The block is accelerating perpendicular to the incline also. Okay, this y component of acceleration is there for the block, which I have shown in red. So now can you say N1 is equal to mg cos theta when the wedge is accelerating?
Sir, I think it'll vary.
It will not be the same because had N1 balanced mg cos theta, it should not have accelerated in the y direction, perpendicular to the surface. But it did with respect to ground. It is accelerating in that direction also. Vanilla,
Sir,
do you? Yeah, continue.
so let's say like the block is in the same situation, the block is sliding, and mg cos the angle keeps changing, right? Theta keeps changing. So
No,
will N1?
that's a different question. Do you want to make theta change? In this case, theta is not changing. It's a solid
Oh
wedge.
yeah, yes sir, yes sir.
Wedge angle made by the wedge is fixed, but the angle in which the block moves will be different because the wedge is going away. In fact, in this situation itself, in the main diagram itself, you all can think and answer. Suppose this system was held with two hands. Let's say one hand is holding the wedge and one hand is holding the block. You release the block. Okay, listen carefully, all of you. You release the block and quickly pull the wedge aside. What will happen to the block?
The block will fall like right wherever it was
The block
supposed to.
falls vertically
Wherever.
downward. Yeah, you
Yes
should
sir.
say it falls vertically downward. If the wedge is suddenly pulled to the left with a high acceleration, the block can even go down straight like this. Okay. Suppose you don't pull the wedge back that suddenly, but you pull it back with some acceleration, then you can make the block go this way, as seen from ground. You pull it with an even lesser acceleration, you can make it go this way. You don't pull it at all, you keep the wedge fixed, then the block will go this way along the wedge. okay, along that angle theta. If you accelerate the wedge forward, you can make the block go like this also. Obviously, had the wedge stayed there, the block would have slid down the wedge following this path. But if the wedge moves forward, then the block also will have to get some forward acceleration, extra forward acceleration. Then it will go like this. If you give it enough acceleration, you can make it go straight like this also. Means you can prevent it from coming down altogether. That is possible. Okay. Anyway, let's work on this problem now. So some things that were cleared now is that when the surface on which the block is lying is accelerated, normal force doesn't balance the weight component. Okay, that is one thing you learned. N1 is not mg cos theta. And you know that the wedge is going to accelerate to the left. Let's call the wedge's acceleration as A2. Block's acceleration is A1 in some random direction. We still don't know the direction also. It won't move at an angle theta. It will move at an angle greater than theta. Okay, this red arrow makes an angle more than theta. And that is the direction of acceleration of the block, which we don't know yet. Let it be. At least tell me which force is greater, N1 or mg cos theta. You imagine how the block is moving.
Theta, sir.
Correct, correct. How did you conclude that?
Sir, because the block is moving down.
It is accelerated perpendicular to the incline downwards. Means mg cos theta is greater than N1. Correct. Okay, so here also you can build some ideas. If mg cos theta is greater than N1, I'll take 3 different colors. Let's say the blue one. If mg cos theta is greater than N1, the block goes at an angle like this. If mg cos theta is exactly equal to N1, the block goes along that orange dotted line this way. If mg cos theta is greater than N1, okay, sorry, greater case is the first case that we took. If mg cos theta is less than N1, that means N1 is stronger than mg cos theta, then the block will go like this. It may be pointed down, it may be going horizontally, it may even rise up. We'll discuss all cases, okay? So many possibilities are there, and in this case, we know what is going to happen. Fine. The question now is to calculate the accelerations of the blocks, block and wedge. For wedge, writing the equation is easy, but deriving acceleration, we'll see if it can be done. Tell me, all of you, what makes the wedge accelerate? What means which force? Which force makes the wedge accelerate to the left? Let us go back to the free body diagram. Yeah.
Pseudo force.
Pseudo force.
No, N1.
N1's horizontal component, not N1 completely also. Okay. Fine. Listen, all of you. Let us imagine a horizontal line here. If this angle is theta, this will be theta. Then this will be 90 minus theta. We don't know how much is N1, so let's call it N1 itself. What will its x component be? Or how much will its x component be? In terms of N1 and theta.
N1 sin theta.
Sin theta, because the angle is 90 minus theta, the x component becomes N1 sin theta. Correct. Theta is given in the problem. N1 is not known yet. It's not equal to mg cos theta. That much we could tell. Okay. So the wedge accelerates under the influence of N1's x component. So for the wedge, if you write F net is equal to mass into acceleration, the net force acting on it is the x component of N1. I'll call it as N1x. Its mass is 2m and its acceleration is A2. And N1x was nothing but N1 sin theta is equal to mass of the wedge multiplied with acceleration of the wedge. This is one equation we have, but there are two unknowns in it. We don't know N1. We don't know the acceleration of the wedge also. Wedge accelerates due to N1, so both are unknowns. Okay, we'll need one more equation. Obviously, we'll have to write the equation for the block. Now, how could we write the equation for the wedge so easily? Because we knew in which direction it accelerates. We knew the angle at which it accelerates. Do we know The angle at which the block accelerates. It's not theta, that much we can say. But do you know the exact angle at which it is going to accelerate? Anyone? If you know, you tell me, we'll write the equation along that direction, we'll get the answer. What do you say? Can you tell the angle at which the block moves? Okay, you are not saying anything. That means you can't say. And that is correct. I also cannot say. Then it becomes difficult to write Newton's second law equation. Because Newton's second law equation, we write force in a particular direction, net force in a particular direction is equal to mass into acceleration in that particular direction. Now we don't even know the direction here. So we can't take components. We can't simplify this. Becomes too complicated. One lengthy way to solve is to assume this angle is alpha, unknown angle. Okay, if this angle is alpha, this angle will also be alpha. Parallel lines, transversal and all. Then you will have to split the motion of the block M into two components. Force this way is equal to mass into acceleration this way, and force this way is equal to mass into acceleration this way. Then you'll have to get that acceleration, this acceleration, combine them, you'll get the net acceleration. Can be done. It's a lengthy process, but can be done. What all unknowns will be there in this? Let's say the block's acceleration in this direction is ax, in this direction is ay. Okay, I'm just telling you one idea. We are not going to follow this. Let the accelerations be ax and ay. What gives ax is mg sine theta. Like it arises from mg sine theta. That's the only force acting that way. Okay, when seen from ground reference frame. So that acceleration we can easily find out. Net force we know for sure. Divide by mass will give you that acceleration. Done. Next, we need the y component perpendicular to the incline. Perpendicular to the incline, we have decided that mg cos theta is stronger. So we should write mg cos theta minus the normal force N1 is equal to mass of the block multiplied with acceleration in that direction. N1 is unknown. So there's one unknown here. There's another unknown here. Okay. So this equation gave us ax value. So we have used this equation already. Second equation. This is the third equation. And what was the first equation? This one. Three equations are there. There are four unknowns. N1, A2, A1. Okay, A1 is nothing but AX and AY. We took it as two components. AY. Four unknowns are there, three equations are there. We had come across such situations before also in laws of motion, where Newton's laws or Newton's second law is not sufficient to solve a problem. There, what additional equation did we use to write? Anyone? Okay, I'll remind you some.
Constraint equation.
Good, good. In those connected body questions, right? If you apply Newton's second law to all the moving blocks also, you will still be falling short of one equation. That additional equation used to be the constraint relation. Okay. Sorry. In this case, see, constraint means restriction. Restriction means what? If one part of the system doesn't move, the other part shouldn't move. Or how one part of the system moves depends on how another part of the system moves. In this case, is there a constraint or not? It's definitely there. We have already visualized that. If the wedge is fixed, block moves in one manner. If the wedge moves, block could move in different manner. Okay. So yes, there is a relation between how they move. But how to write that equation? How to derive? In connected bodies, blocks connected by strings, we used to use the idea that length of the string should not change. So if the string gets shortened on one side by some x, then it should elongate on the other side by the same value x. So x is equal to 2y. We used to get relations like that. What to do in this case? How to relate the motions of the block and wedge? Any idea, anyone? The idea can be obtained from this diagram. This visualization, if you do properly, you may get an idea. Anyone, any idea how to relate the motion of the block and the wedge?
Sir, I think A2 should be equal to the acceleration of M in the x direction.
X means this. Like we call this as X. Is that what you're saying?
No, sir, like in the horizontal direction.
Horizontal, okay, means fine. See, the actual acceleration of the block is shown by that blue vector. Okay, let me highlight this a little bit. Right, that's the actual acceleration of the block. Yeah, it has an X component, horizontal component, this one. So Vanilla is saying, if you call the overall acceleration of the block M as A1, then A1's X component should be equal to A2. Why? Why should it be like that? Any reason why you think it should be like that? Others think about the question, how to connect the motion of the block and motion of the wedge. Is there anything common to them, or how are they related? Okay, Vanilla, this is not correct, because we have visualized this also. If the wedge is suddenly pulled to the left with a lot of acceleration, you know the block is going to fall straight down. In that case, it won't even have an X component, but this has a large X component. How can you say this is equal to this? Okay, no, that is not correct. Any other ideas, anyone? We need to relate the motion of the block and the wedge. Okay, actually, this is what makes physics questions all the more difficult. You can write equations based on how the system moves. Now, the block moves in some odd direction like this. We don't know the angle yet. But does the block stay in contact with the wedge or not? We are not pulling the wedge. I mean, an external force is not pulling the wedge. Wedge is moving because the block is pressing it. So, as the block slides down and the wedge moves to the left, do they remain in contact or not?
They do, sir.
They have to. Okay, they do. They do. So, remember, you can convert this into an equation. Two surfaces remain in contact means, okay, let's take a simple case first. Put one block on this. Tell me, if the block has to remain in contact with this horizontal surface, what are the possible ways in which it can move? If the block has to remain in contact with that horizontal surface, can it move? If yes, in which direction could it possibly move, staying in contact with the surface?
It can move horizontally.
Horizontally, right, left, out of the screen, into the screen. You imagine in 3 dimensions, it can move anywhere on the floor, staying in contact with the floor. Others, why are you not responding? Why is it so difficult to visualize that? Okay. Now see, the surface has zero acceleration in the y direction. Okay, y is vertical. Then to stay in contact with the surface, the block also should have zero acceleration in the y direction. Means these two should be equal. Let's go back to what we discussed in the last class, elevator case. Let's consider that situation where the elevator is accelerated upward. When elevator is accelerated upward, the block also accelerates along with the elevator. No, it's on the floor of the elevator. It has to go with it. The block stays in contact with the floor. For the block to stay in contact with the floor, what is the block's acceleration? We solved the equations also. What acceleration did we assume? Same acceleration as the elevator. Okay. And we took that case also. While coming down, if the elevator goes with an acceleration more than g, what will happen? If the acceleration of the elevator is more than g and the block's acceleration is only g, then they lose contact. Okay. So how do we put all this together or make use of all this in writing equations and solving that problem? For two surfaces to be in contact, not just this wedge problem, generally I'm telling you. For two surfaces to be in contact, along the perpendicular drawn to them, okay, which is like this, which is what we are calling as the y-axis in this case. Along the y direction, okay, you all imagine this as the y-axis for this situation. So in a direction perpendicular to the surface of contact, there should be no relative motion. Means along the y direction, they must have equal velocities, equal accelerations also, only then they will stay in contact. Okay. Now the wedge has an acceleration a2 to the left, which is not calculated yet. Acceleration is a2 to the left. Will it have a component in the y direction or not? It will. Y direction is not making 90 degrees with it, so some component will be there. Wedge's acceleration in the y direction, I'm calling it as a2y. Okay. And block's acceleration in the y direction, we called it as ay already. I won't change the name. No use changing the name. So block's actual acceleration is along that thick blue arrow that I have shown, but it will have a component of acceleration this way. Ay. And these two must be equal. Only then they can stay in contact. Along the surface, block can slide as much as it wants, but perpendicular to the surface, it should move along with the wedge. Otherwise, it will lose contact with it. Okay, so we are making an equation out of it. The wedge's acceleration in the y direction should be equal to the block's acceleration in the y direction. That is the constraint here. Okay, now we have to take components and make that fourth equation and solve for all the unknowns. This angle is theta. This will be 90 minus theta. So A2's y component will be A2 sine theta. You can write that as equal to AY. This is the fourth equation. We had four unknowns. We got four equations. You can sit and solve. That is one way to solve this problem, but understand what we have done here. First, we considered forces acting on the system, both block and the wedge. And under the influence of those forces, we determined how the system is going to move. We know for the wedge, it was easy to tell. Wedge is not allowed to move vertically, but N1 is there with a horizontal component. So wedge moves to the left. That we could easily tell. And if wedge moves to the left and the block has to stay on the wedge, then block cannot move along that angle theta. It has to move along some other angle. That also we visualized. Okay. Then we applied Newton's second law to both of them carefully. Wedge is moving in the x direction, so we wrote net force in x direction is mass into acceleration. Block is moving in some random direction, which we don't know. So, okay, we didn't make use of alpha, never mind. But we split its acceleration into two components. One along this, the dotted line theta, angle theta. The other component perpendicular to it. So these two components were unknown. Acceleration of the wedge was unknown. Normal force between the block and the wedge also was unknown. Four unknowns were there. We wrote Newton's second law for the wedge, one equation. We wrote Newton's second law for the block in two different directions, two more equations. The last equation we wrote is the constraint equation. So 4 equations enough to solve, can be done. But as I said, this is the lengthier way to solve. But I want you all to solve this. See, your understanding will improve, your application of Newton's laws will improve. So not just in this class, generally also, if someone explains to you how something has to be done, don't just listen and say, okay, now I got it, I'll be able to apply. No, you won't be able to apply unless you put your pen down and solve the equations. You will not learn anything. Fine. So it is important that you apply. I want you all to, like, I'll send you the notes of this chapter. I want you all to solve these equations and get the answer. If you want, I'll simplify the problem a little bit. We'll assign some numerical values for mass, and theta will take 37 degrees. So equations will be a little comfortable to solve instead of m, theta and all. We'll do that. Let me explain the other way to solve.
So can you show the third equation once? I just want to note it down.
I'll send you the notes anyway. Okay. Third equation was Newton's second law applied to the block in a direction perpendicular to the incline. That is the y direction. In that direction,
with respect to the y-axis, right, sir?
With y components. Yes. Mg cos theta was acting in the negative y direction. N1 was acting in the positive y direction, but it was accelerating downward. So we wrote mg cos theta minus N1 is mass into y component of acceleration.
Okay, sir. Okay.
Okay. Let's do it the slightly easier way. The main difficulty in solving this problem in this method was that we didn't know the direction in which m is moving. Okay, or m was going to move. There is a way to avoid that, okay, or bypass that. Can you all tell for sure which way 2m is going to move? With respect to ground, as seen from the ground, how is 2m, the wedge, going to move?
Negative x direction.
To the left, negative x direction, correct. That is known for sure. Okay. But its acceleration is not known. We know it will move to the left, but with what acceleration, we don't know. Let's call it as A2 only. And we have one equation for it. N1 sine theta was giving it that acceleration. So 2m into A2. Okay. Now, when you observe from the ground, the block moves at a random angle like this. But suppose you make the wedge the reference. Wedge is going to the left, okay. But suppose you are standing on the wedge. Let's say it's a very large wedge and you are standing on it. So with respect to ground, the situation would be like this. I'll write it here. I want you all to imagine how it would look if you are standing on the wedge. How will the block appear to move? If wedge is made the reference, wedge won't move in that frame at all. So this will be fixed now in that frame of reference. How will the block appear to move relative to the wedge?
Downwards.
Down and incline.
Like along the inclines.
Okay. Down the incline, you should say down the incline. Do you all agree with this or not? Relative to the wedge, does it slide parallel to its surface or not? It does. You can see here also. Like it always stays in contact with the wedge, no? So the only way it can slide relative to the wedge is along its surface. It's not digging into the wedge. It's not jumping off from the wedge. It is sliding on the wedge only, always. So if you make the wedge the reference frame, the block slides like this. But this is not its original acceleration. This is the direction in which it moves relative to the wedge. So we can say this is the acceleration of block with respect to wedge, not its original acceleration. Is this point clear to all of you?
Yes, sir.
Aishwarya, did you understand?
Yes, sir.
Pawan?
Yes, sir.
Okay, okay. Yusuf, is it clear? Okay, if you cannot unmute, you type. Right. Now we know the direction of motion of the block for sure. Okay, not with respect to ground, but with respect to the wedge, we know for sure at what angle it is moving. It is moving at an angle theta. That is the advantage we have if you make the wedge the reference frame. But let us go back to the ground reference. Is the wedge accelerated with respect to ground, or is it non-accelerated? With respect to ground, is the wedge accelerated or non-accelerated?
It is accelerated.
Accelerated, sir.
It is accelerated. Which way?
Negative x-axis.
Left. By what acceleration? A2. We called it A2. We don't know how much it is, but we called it A2. So if you are observing something relative to that wedge, what kind of a frame of reference is the wedge now? It is accelerated relative to the ground. So what kind of a frame of reference do we call it?
Non-inertial frame of reference.
Non-inertial frame of reference. And when you observe things with respect or relative to a non-inertial frame, but you want to explain things in terms of Newton's laws, what should you do?
We should consider pseudo force.
You should consider an additional force called pseudo force to be acting on the object. Okay. You know wedge accelerates to the left with an acceleration A2. Vanilla, don't answer. Anyone else answer? How much pseudo force should we consider on the block and in which direction? Recollect the formula for pseudo force. Recollect the direction in which pseudo force should be applied.
2m into a2.
Correct. No, 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 no.
2m into a of block. This
No,
one.
we don't know A of the block, no?
No, sir, I'm talking about this one. The a.
Wedges.
Yes, sir, that one.
So that is 2m into A2. You said that.
Oh.
But no, what is the general formula in this case? Leave about this case. Anyone can tell. What is the general formula for magnitude of pseudo force?
Mass into acceleration of non-inertial frames.
Whose mass?
Mass of the block, sir.
Mass of the object on which you are applying the pseudo force. Now here, wedge is the reference. On the block, you have to consider the pseudo force. So magnitude of pseudo force is mass of object, that is m, multiplied with acceleration of frame, that is a2. Wedge's acceleration was considered a2 with respect to ground. Okay, I knew Vanilla can answer, but others are not answering at all. Don't know why. Anyway, what about the direction of pseudo force? In which direction should it be applied? Magnitude is clear.
Opposite to the direction of acceleration of non-inertial.
Correct. So here wedge is the frame. Wedge is accelerated to the left. So pseudo force on the block should be applied to the right. So you need to consider a force mass of the object multiplied with acceleration of the frame of reference to be acting this way. Okay, let's just call it FP, pseudo force. Its magnitude is known to us, m into A2. This force should be considered if you want to explain things by applying Newton's laws relative to the wedge. Okay, there are obviously other forces acting on it. What other forces act on it? It's mg cos theta, mg sin theta, those things will be there. Why is it thick? Just a moment. and down the incline. Okay, this is acceleration. The direction of acceleration we visualized. We'll come back to that. This is the force, mg sine theta, and there will be a normal force also acting on it. Okay, initially we had shown all forces in orange. Never mind. This is N1. And under the influence of all these forces relative to the wedge, the block accelerates in this direction, which is what we called as the x direction. Let me take the x-axis here. X-axis is parallel to that surface. Y-axis is perpendicular to the surface. So under the influence of all these forces, the wedge accelerates along the x-axis. Not wedge. The block accelerates along the x-axis relative to the wedge. In the y direction, the block has no acceleration relative to the wedge. Okay. One of you tell me, what all forces are there in the y direction? Y direction, like upward or downward, both ways you tell. What forces are there?
N1 mg cos theta.
Okay, incomplete. Anyone else? What all forces are there in the y direction?
The y component of
Pseudo force. Correct. Rishi, that pseudo force is not completely along x-axis, it's not completely along y-axis also. So you'll have to take its components. Okay. So pseudo force component will act this way. Now you can also explain why mg cos theta is stronger than n1. Okay, mg cos theta is balancing n1 and also pseudo force is y component. That's why mg cos theta is more than n1. And that pseudo force will have an x component as well. This way. That will add to mg sine theta and make the block accelerate. So now you don't have to consider the original force, pseudo force. Like when you take components, don't take the original force. Right? So F net in the y direction should be 0. Because perpendicular to the incline or perpendicular to the wedge, the block does not move when the wedge is the reference frame. So you all tell me, how do we write this equation? What I mean is, which force balances which force? I already told you the answer. What forces are acting in the positive y direction?
What are the components of pseudo force and the normal force?
So N1 plus that component of pseudo force. See, this angle will be theta, parallel lines transversal. This will be 90 minus theta. So that component of pseudo force becomes MA2 sine theta. And these two should have been balancing mg cos theta. We got one equation here. One equation, or this is the second equation, right? Where was the first equation? First equation was written with respect to ground for the wedge. Okay. And net force in the x direction gives it the acceleration m into acceleration of block with respect to wedge. Tell me, what all forces act in the, or what is the net force acting in the x direction in this case on the block?
mg sin theta plus MA2 cos theta.
Mg sin theta plus pseudo forces component, that is MA2 cos theta, and these two together provided the acceleration of block with respect to wedge. Okay, now how many unknowns are we coming across? N1 is unknown. Wedge's acceleration A2 is unknown. N1 unknown. wedge acceleration, original acceleration of the wedge A2 is unknown, and acceleration of block with respect to wedge ABW is unknown. Three unknowns, we have three equations. Enough to solve. Okay, so from these, solving these three equations, see, I don't expect you to solve these exact equations because sine theta, cos theta, very lengthy expressions you have. So solving these equations, you can get N1, you can get acceleration of the wedge, original acceleration of the wedge you can find out, and acceleration of block relative to wedge you can find out. And generally, acceleration of B with respect to W is original acceleration of B minus original acceleration of W. If you know this, and this you substitute here, acceleration of the wedge, you can tell what is the original acceleration of the block. Okay, so basically when we made like this in the second method, what we did was we made the wedge the reference. What is the advantage we have by doing this? One thing, visualizing motion of the block became easy, writing equations became easy, and what do we say? There were three equations that were to be solved, three equations, three unknowns, slightly easier method to solve. Fine. So I'll send you the notes. What I want you all to do is solve this same problem both ways, but I'll give you some numerical values. I want answers from all of you. So this itself will be your worksheet for tomorrow, day after tomorrow. I wanted to ask you all, we missed one class. Can you all attend class tomorrow? Like I am assuming tomorrow is a holiday for all of you. Do any of you have school tomorrow? No. Okay. Can you all attend class from 1 to 2:30 in the afternoon?
Yes, sir.
Yes, sir.
Yes, sir.
Aishwarya, what about you?
Yes, sir.
Okay, so tomorrow 1 to 2:30 we'll have one class. We'll solve some more problems based on pseudo force and conservation of linear momentum. So yeah, I want you all to solve this problem. So you know how to approach and all. So just apply what we discussed today. Assume the block's mass is say 2 kg. Wedge mass is 4 kg. Angle theta is 37 degrees. Calculate their original accelerations with respect to ground. Okay. So by or before tomorrow's class, you solve this. Okay. Fine then. So today what we discussed was basically application of pseudo force in one case to calculate the acceleration. These are difficult questions, but see, the first time you see it, this is difficult, but this has been asked in exam so many times that this question is now a routine question. Okay, so you have to get used to all this. Fine, thank you all. If you have any doubts, you can ask. I'll send you the notes immediately. Lecture will be uploaded later, but I don't think you'll need the lecture anyway. Okay, if possible, I'll send that also before like maybe 10 o'clock.